Hello, I'm Dr. Matt Whiteley from MZA Associates here in Dayton, Ohio. And today I'd like to talk with you about some recent testing that we did and follow-up analysis of data called the Eclipse Turbulence Evaluation and Sensor Testing, or eTEST for short. I'd like to acknowledge the participation of my collaborators, Dr. Eric McGee, Dr. Jason Schmidt, and Dr. Yakov Diskin, who all contributed to this talk that I'm going to give, and also others at MCA, including Richard Dry and Kevin Jakovitz. This talk is for the propagation through and characterization of atmospheric and oceanic phenomena, or PCAOP, which is an Optica conference to be held in July of 2024 in Toulouse, France. I'd also like to acknowledge the help of our collaborators at the Air Force Institute of Technology, who volunteered some of their sensor equipment for the testing and also helped to get this approved for public release from the 88th Air Base Wing Office of Public Affairs. So in terms of the talk today, I'd like to first tell you a little bit about the eTEST activity in terms of what it's all about, and then go on to tell you about some of the targeted sensors that we set up, and then go on and show you what the data look like during this test. So the Eclipse Turbulence and Evaluation and Sensor Testing, or eTEST, was really about making continuous turbulence and weather measurements before, during, and after the total solar eclipse that occurred on the 8th of April of 2024. This was similar to some testing that we first did in 2017 and reported in a prior Optical Society conference in 2019, where we saw that the eclipse indeed did produce a significant reduction in turbulence. But this was actually a partial solar eclipse in Dayton at the time. We had about a 90% obscuration occurring for the sun, whereas this time we were along the path of totality. So this was an opportunity to use those same sensors and to take advantage of some of the new developments that had happened in the interim. We'll tell you about that in a little bit, and we were able to involve other organizations who are also operating Delta WX sensors, both within MZA and outside of MZA, and in some of our affiliate organizations. So the key development that had happened since that 2017 testing was the development of the Delta WX deep learning turbulence sensor. Here's an image of the sensor. This is what it looks like in its standard configuration. It puts together a Delta imaging turbulence monitor with a standard weather station, and then the processing of that weather and turbulence data together. Each day, the sensor goes about archiving its results and then applies machine learning in order to come up with a weather-driven turbulence model. And then it goes off and automatically, with a network connection, downloads numerical weather forecast data, and then can give you a forecast of turbulence conditions that are upcoming. With a network connection, it can also write to an online archive, and we'll show you a little bit about that here later. So this really is the go-to weather turbulence sensor. And as you can see here from our map of these sensors, we have them deployed in what is called our Weather Intelligence Network. And that's a collection, obviously, of Delta WXs that are deployed around the country with network connections. And we're showing you this map of where they're located, and overlaid on that is the path of totality for the eclipse. So you can see that pink band, that's the path of totality. And then we're showing you contours of different amounts of eclipse that would happen on the 8th of April. And so we had sensors deployed across the country, and this really was a nationwide event. Everyone from coast to coast saw a certain amount of eclipse. But to draw your attention to right here in Ohio, Western Ohio, where we have several of these sensors placed that were relatively close to the line of totality. Showing you a little bit more detail here in Ohio. We just happen to be in the Dayton area, which according to the projections, had about 2 to 3 minutes roughly of totality that would be experienced. And most of our sensors that are located in the metropolitan Dayton area were experiencing about 2 minutes and 30 seconds of totality. We did see an opportunity if we could go just a little bit west of Dayton, we could get over the 3-minute mark. But if we wanted to get closer to the 4-minute mark, then we needed to go north. And so that's what we ended up doing. And I'll tell you a little bit about that sensor placement where we got as close as we could to the path of totality. So let me just show you some of the beautiful images that were taken during the eclipse. This is just sort of a time lapse going from initial point of contact all the way through totality. The images in the middle here of totality were taken by my colleague, Dr. Adam Smith, beautiful images that he captured, and then coming out of totality. So very simple setup, and this was quite a phenomenon to observe. Darke County Airport represented a very good location in order to make turbulence measurements during the eclipse because it's located only about 10 kilometers away from the center of the path of totality. And it is a public space. It's a county airport, and we had great cooperation from the manager, Mr. Scott Noss, from Darke County Airport. We talked with him about it, and he invited us to place a sensor at in the vicinity of their new terminal, and we placed our target board downrange by 780 meters, which you see here in the images. That was the initial deployment. A little bit later, we brought in some particle counters where we could also look at aerosol concentration changing. And this sensor was put in place about 2 weeks, about 3 weeks before before the total eclipse, and then remained through the month of April installed so that we could get that weather-driven turbulence modeling at this particular site. So I'm going to show you this video, and I'll just let it play, and I'll kind of speak to it as we go along. This is showing you images on the right-hand side of the target board as we go towards totality. You're going to see totality coming in here, dark, obviously, and then coming out of totality and the sunlight coming back. That blue line on the plot is the solar irradiance as a function of time, and the pink line is the actual turbulence level. As it plays again, we're going to concentrate more on the turbulence level. We started off around 10 to the minus 13, which is a typical turbulence level. And as the eclipse progressed, we went through a minimum or a neutral event. As we entered totality, we got to a local maximum. And as we came after totality, we went back to a minimum before coming back up to a higher level of turbulence that would be typical of that late afternoon. The eclipse event occurred from about 2 o'clock in the afternoon and ended at about 4:30. So this is interesting to look at here because the strongest turbulence didn't occur before or after the totality. It occurred during totality. And we had these interesting neutral events or low turbulence events that happened prior to the totality and then after totality. And that was a little bit of a surprise as we saw this unfold because our prior measurements during the partial eclipse in 2017 just indicated a general reduction and quite a significant reduction in turbulence, but we never saw this effect of having neutral events on either side of a local maximum at totality. So hang on to that thought because we're going to see that again happen. And if I look a little bit more detail about when those events were occurring, the pre-eclipse neutral and the post-eclipse neutral here at time B versus time D, you'll see that they're a little over an hour apart for those neutral events. And they're mostly placed symmetrically with respect to the time of totality, which was 15:10. So about 3:10 in the afternoon at Darke County Airport. And so about 30 minutes before that and about 30 minutes after is when we experienced those neutral events, which were clearly visible within the turbulent imagery. We had another sensor that was operating a little further south, and this was at Dixie High School in New Lebanon, Ohio. And this is a great example of having a fabulous collaboration with the New Lebanon School District So we appreciate them allowing us to come in and install a Delta WX sensor. Turns out we were able to install the sensor in their press box at their sports stadium, and then image a target that was located on top of the school at about 440 meters distance from the sensor. So this sensor experienced 3 minutes of totality and was another really great reference point. This one got installed enough in advance where we could get a good converged turbulence model at the time of the total solar eclipse. I'll let this play out a little bit so you can see this video. It's very similar to what we saw at Dark County, where we see pre-eclipse and post-eclipse neutral events, and then we see a maximum that's occurring near the time of totality. Totality is not quite as impressive here because of it's shorter, but still the same kind of effect that we saw. And key points and timing, the images that are associated with that effect of the eclipse on the turbulence. This data, though, let us look a little more carefully at what was driving these neutral events. And the thing that we immediately recognized is that if I look at a full day's worth of turbulence, I can see the morning and the evening neutral events. These are typical events that happen day by day, and they're fairly predictable. So the morning neutral event, the evening neutral event, morning is neutral is very easy to see. But if I look at the irradiance level, which is around 200 watts per square meter, where that morning neutral event occurs, and if I trace over to the time of the eclipse happening, one thing that I can see is right about where the solar irradiance equals the solar irradiance for the morning and neutral event, I get these neutral events that occur on either side of the total solar eclipse. So when turbulence is when the irradiance is at that level, turbulence is going to reach a very low level. If it's less than that, it actually is a very unstable condition, and that unstable condition then leads to that rise of turbulence. The other thing we consistently saw was the post-totality neutral event ended up giving a little bit lower turbulence than the pre-totality event. And we attributed that to a sort of a lag in temperatures that you can see on the lower right-hand side here, where the temperature dropped, but it reached its minimum a little bit after the time of the total solar eclipse. And if I look at the other sensors that were located on the line of sight, we see that effect repeated on many of the sensors, not all, but they're all experiencing this eclipse W, and that was the unifying observation for all of the sensors that were on the path of totality. I contrast that with this sensor, which is at Eglin Air Force Base, which is on the Gulf Coast of Florida in the Panhandle. And if you look at, in this case, it was only about a 75% partial eclipse. And in this case, what you'll see happen here is definitely a reduction in turbulence. The image is becoming clearer and clearer, but we do not see the pre-eclipse neutral or the post-eclipse neutral. We simply see a reduction in turbulence all the way through the time of the max, and then an increase in turbulence after that. And so it's much more similar to what we experienced during 2017 partial eclipse in Dayton, Ohio. So in terms of our overall conclusions, this was a great success for the eTEST. This was a great unprecedented opportunity for weather-driven turbulence measurements and modeling. It demonstrated the Delta WX sensors and the network that we have with the Weather Intelligence Network for unique weather-driven turbulence observations. And the real-time monitoring that happened across the nations, these results were immediately available. In fact, I myself was watching all of it unfold on about a dozen sensors during the eclipse. And the thing that was most striking about the test results was that the sensors on the path of totality consistently exhibited this eclipse W effect, which consists of a pre-eclipse and post-eclipse neutral events, followed by stronger turbulence or with stronger turbulence during the time of totality. The asymmetric pre and post-neutral events were related to lagging of air temperature as it's affected by the actual eclipse. And those neutral events appear to have been coming at times when the solar radiance was equivalent to the regular morning and evening neutral events. And this was much less likely to happen for any of the sensors that were outside of the path of totality. So I hope this presentation has given you a good idea about what the eTEST was all about, and that piqued your interest. And I appreciate your attention during this presentation. And just to point out that this presentation, the video included, is approved for public release. The distribution is unlimited. I'm Matt Whiteley from MCA. I thank you and take care. Bye-bye.